Hello and welcome to our next vectors lesson, and today we are looking at the dot product. So we are looking at both algebraic and geometric interpretations of the dot product, but we will start with the geometric. So the dot product is actually also called the scalar product, and we'll see shortly why. So given two vectors OP and OQ, and the angle between them, which is theta, and theta is between 0 and 180 degrees inclusive, then we say the dot product, and it is shown with that dot in the middle, is the magnitude of OP times the magnitude of OQ times the cosine of theta. But this is a scalar, and this is a scalar, and this is a scalar. So the result of the dot product is always a scalar, and that's why it's also called the scalar product. Now let's interpret this for different values of theta. So if theta is between 0 and 90 degrees and inclusive of 0, then the cosine of theta is greater than 0, so the dot product is greater than 0. Now, if the angle theta is equal to 90 degrees, then the cosine of theta is 0, so then the dot product is actually also equal to 0. And if theta is between 90 degrees and 180 degrees and equal to 180 degrees, then the cosine of theta is less than 0, so the dot product will also be equal to 0. The reason for this also is because the magnitudes are both going to be positive values. So really, what determines the sign of the dot product is cosine of theta. Now let's see what this looks like visually. So if we have OP, vector OP here, and OQ here, then, and this is the angle theta between them, then we say that the dot product of OP and OQ, which is defined as such, is actually telling us how similar the direction of the two vectors are. And so I've actually included a simulation for you on Google Classroom to see the dot product with different vectors. So hopefully that makes a little bit more sense. Play around with it, move the vectors, see once their direction is closer, then you have a greater value for the dot product. And when they're completely, or like the angle between them is greater, so their difference in their directions is greater, then you're going to see a different value for the dot product. So throughout this lesson, we're actually going to be doing an investigation style of calculations where we're looking at the different properties of the dot product, but through different examples. So starting with this first example where we have vector A with magnitude 5 and vector B with magnitude 8, and the angle between them is theta and equal to 60 degrees. So first we're calculating A dot product B, and then we're calculating B dot product A. So the dot product of A and B is the magnitude of A, magnitude of B times cosine of 60 degrees, which is equal to 5 times 8 times half, which is 20. Now, if you have B dot product A, now all we're doing is switching out the magnitude, so starting with magnitude of B and then magnitude of A. But multiplication is commutative, so 8 times 5 is the same as 5 times 8, so that's why we get the same answer. So really, we have shown also that the dot product is commutative, which means that A times B is equal to B times A. But is this true for any two vectors? Why or why not? What do you think? And I hope you do conclude that yes, it does hold for any vector because really when you change the order of A and B, all you're doing is changing the magnitude of changing the order of the magnitudes, and these two are scalars. And because we have a commutative property for multiplication of scalars, then really the two outputs are going to be the same. So then yes, this is equal to this. Now, the second one, we have the same two vectors, but now we are calculating A dot product with A and the dot product of B and B. So the angle between a vector and itself is actually theta, which is equal to 0 degrees, and cosine of theta is equal to 1. So then the dot product of A by A is just the magnitude squared because cosine of 0 is just 1. So then we have 25. And the dot product of B by itself is also the magnitude squared, which is 64. And this is actually the maximum value of the dot product that you will see here for A because remember cosine of theta as a whole is between -1 and 1 inclusive. So, but specifically because we're looking at the angles between 0 and 180 degrees, then in this case, cosine of 0, which is equal to 1, gives us the maximum value here for the cosine. And so this value is maximized, which is telling us that the vector in comparison to itself, remember the dot product is telling us how similar the directions are, then this is the maximum similarity that we can have because it's going in the same direction. So now, what can we conclude about the dot product of a vector, any random vector v with itself? And I hope you see here that we can conclude that that oh, v dot product v is the magnitude squared. And maybe I'll add here for you as well. From here, we concluded that a dot b is equal to b dot a. And so I do have a list of all of these properties later in this lesson, but I'm just showing you example by example the conclusion that we're reaching. Now, in our third example, so we're still using the same vectors A and B as above. So remember, vector A has a magnitude of 5, vector B has a magnitude of 8, and theta, which is the angle between them, is 60 degrees. So now we're told we have a third vector C, and its magnitude is 4, and it has an angle between the angle between B and C is 20 degrees. So keep in mind, oh, I do have. So I'm going to show you first. So let's say this is B and this was A. And this angle was 60 degrees. Now we have the third vector here, C, and this is the angle that's 20 degrees. So really the angle between A and C is 80 degrees here, but we can conclude that from this diagram here and just based on these two different angles that were given. So here we're just first asked to find the magnitude of B plus C. So I'm going to set up the triangle diagram for the addition. And in this lesson, I've also included vector calculator for you where it shows when you're adding different vectors, how it will look like from head to tail. So please take advantage of that as well. So here, vector B is in blue and vector C is in green. So we know that vector B has a magnitude of 8, and because we're working with geometric vectors, I can choose this to be the position vector. It doesn't really matter where it was, I just care about that magnitude 8. And now here, this is really that 20-degree angle. So here I have 160 degrees, which is the supplementary angle. And C has a magnitude of 4 here, which is half of the magnitude of B. And I want to know what the magnitude of this resultant vector is. So I will just use cosine law here. So cosine law gives me this expression here, or this equation here. And remember, I'm working with this angle, so cosine of 160 degrees. So then we end up with the magnitude of B plus C is the square root of 80 plus 64 cosine of 20 degrees. Now, the reason why I switched here to 20 degrees is because I had negative cosine of 160 degrees. And remember, with cosine, this is one of the properties where I can do negative of cosine of 180 minus this angle, which is now positive cosine of 20 degrees. And so now this square root will give me approximately 11.838, which is the magnitude of the resultant. Now we're asked to find the angle between B plus C and A. So consider the triangle that we form here. So this was A, this is B, and that's that 60-degree angle, and this is vector C with that 20-degree angle. And if I draw my parallelogram here, so this is now C, and this is equivalent to B, then we already saw that this was 160 degrees, and what we're asked to find is the angle between B plus C. So this resultant, which is B plus C, um, and A. So this is different than necessarily the angle of A and C or A and B. We do need to consider this resultant here. And so we have 60 degrees here. All we have to do is find this angle theta here, which is between B and the resultant, and add this to the 60 degrees. So really, we're not using um, anything with A here until the very end. We're actually just finding the complete vector, or sorry, the complete resultant vector of B plus C, because now we had the magnitude, so now we're just finding the angle, and then we're making a conclusion based on the fact that B made an angle of 60 degrees with A. So let's apply sine law here now. So the sine of theta over the magnitude of C, and that's this opposite side length here, is equal to, and remember this is just 4. So this is equal to the sine of 80, sorry, slight error there. That should have been sine of 160 degrees, because this is this angle and its opposite side length, which is the magnitude of B plus C, which we had found above. So I am using, in this case, the exact value, not the approximate value, just so I get a better value for my angle here. So then I'm solving for sine of theta here. So theta is actually the inverse of this fraction here times 4, which was the magnitude of C. And I get an angle of approximately 6.6363 degrees. So then we say the angle between A and B plus C is now that's 60 degrees plus theta. So remember, theta was just this angle here. So this is 6.63 degrees. And so then the angle between A and B plus C is 66.63. And you can just leave it at 2 decimal points here. So it would have just been fine to write that. And don't forget degrees there. And now we're asked to find the dot product between A and B plus C. And so remember, we have magnitude of A, now we have magnitude of B plus C, and we have the angle between them, which is 66.63 degrees. So we can find the dot product here. Now, here we have magnitude of A, which is 5, the magnitude of B plus C. Again, I'm using the exact value just to get a more precise answer, but here I've shown you with approximate values as well. And now this angle, which was, you can just go with, at this point, 66.63 degrees. And so, the reason why I did leave it up here as 4 decimal points as well is because, again, this gives me a more accurate answer here with the 4 decimal points. And finally, I see that the dot product of A and B plus C is 23.473 degrees. Or, sorry, not degrees. It's a scalar. My bad. So ignore this. And then also ignore it here. Okay, so next, so remember, this was A dot product with B plus C. And now we're trying to find the dot product of A plus B plus the dot product of A plus C. So this is really distribution here of A with B and then C. And we want to see if we can do that with dot product and whether it gives us the same answer. So here I will find A plus B as the dot product, so what we found above. And then here we're finding the dot product of A and C. And now is where I have to consider that 80-degree angle, which is formed between A and C. And so here you will end up with these two values. And if you calculate them, you actually do also get 23.473. And so what can you conclude about the distributive property from part C and D? I remember here we have this. And what you've done is you've shown that those two highlighted expressions are the same. So then we do have distributive property with the dot product. So if you have A dot product B plus C, then this is the same as taking the dot product with the first vector and the dot product with the second vector that is being added together. And remember, this will be a scalar in the end. This one will be a scalar, and then this is a scalar plus a scalar, so they're both scalar quantities. Now, again, using the same three vectors as above, we're asked to show why this following equation is true. So why can we not do A dot product B dot product C, and why this is also not equal to A dot product B dot product C? So keep in mind here, A dot product of B is a scalar. As we've been saying, this is also the scalar product. So then we cannot take this dot product of a scalar and a vector. Similarly, B dot product C is also a scalar, so we cannot take the dot product of a scalar with A. So this whole thing, to begin with, is flawed. And so then we actually don't even have associativity of the dot product, because that's what it is for an operation to be associative. That's what it's telling us. So if we have, for example, 2 plus 3 plus 4, and we know addition is associative, this is the same as 2 plus 3 plus 4. But in this case, if you have a dot product here, as we saw here, this will be a scalar. So then it does not satisfy the requirements of our dot product anymore. And so that's why this whole thing to begin with is invalid. So then we cannot have these two expressions to be equal to one another. And so we can conclude a dot product is not associative. Now, suppose we have a fourth vector, D, and it creates a right angle with vector A. So now, keep in mind, maybe let me copy this that I had here. Okay. So if I have this here, and now I'm going to add in a fourth vector this way, perhaps there. This is vector D, and this forms a right angle with vector A. And we're asked to find why all of these are equal. So A dot product D is the same as A dot product negative D, or negative A dot product D, negative A dot product negative D. So the reason for this is when these two are perpendicular to each other, so they form a right angle, then the cosine of 90 degrees, as we said above, is equal to 0. So then all of these are actually equal to 0. It doesn't even matter what the magnitudes are or which vector you're using to get the opposite, which vector and its opposite vector you're using to get the dot product. So even if I did negative A this way or negative D this way or any combination of these four, then because cosine of 90 degrees is 0, then all of these are just equal to 0. So then 0 is actually equal to 0 in all these cases, so they are equal. And so you can actually make a conclusion here as well for any two vectors that are form a right angle or they are perpendicular to each other, then their dot product is always 0. Now, for the vectors above, you're asked to calculate the dot product with 0. So it's actually not as complicated as you might think because the magnitude of the 0 vector is just 0. So in this case, any vector you choose, for example, let's say we did A dot product with the 0 vector, then this is the magnitude of A, the magnitude of 0, and the cosine of theta, which is the angle between them. But really, this part is 0. So then it doesn't even matter what the other parts are. This whole expression will be 0. And that's also another property now where any vector, its dot product with the 0 vector will be equal to 0. And so here is that mighty list that we have been working towards, the properties of the dot product. So we have shown a a lot of these, but some again are just conclusions that we can also make really easily from all the work we have done so far, even if I haven't shown you explicitly. So we did see the commutative property. So P dot product Q is the same as Q dot product P. We also saw the distributive property where I can distribute P into an expression where I'm adding two vectors. We also showed this, but now it has a name. It's the magnitude property, where the dot product of a vector by itself is just its magnitude squared. And remember, this is the maximum value for the dot product that you will get in this case. And now we also have unit vector. So this is derived from the magnitude property. So any unit vector, if you take a dot product by itself, because the magnitude of I is equal to the magnitude of j, which is equal to the magnitude of k, and it's equal to 1, then all of these dot products will just be equal to 1. Now we also have associative property with the scalar. So keep in mind that the scalar, you can always just factor it out. And you can actually show this using any of the vectors that we had worked with above. So pick any random scalar and you will see that we do have the associative property with a scalar. So if I have P dot product Q and a scalar K in there, then the K doesn't actually make a difference until the very end. I can just find the dot product of P and Q, which is a scalar, and then multiply it by that scalar K. Finally, this is another one that we did see, which is orthogonality or the perpendicular property, and it has to be non-zero vectors. Because again, if it's zero vectors, we go to this property, but for now, if A and B are non-zero vectors with A dot product B, then the two vectors are orthogonal or perpendicular if they're oh, I think I'm missing this part. If A dot product B is equal to 0. Okay? And again, we saw because cosine of 90 degrees is equal to 0. And our final property as well is the zero vector property. So again, the dot product of any vector and the zero vector, and we can have commutative here, is just equal to 0. So let's see some examples now. If vectors a plus 3b and 4a minus b are perpendicular and the magnitude of a is 2 times the magnitude of b, then determine the angle theta between the non-zero a and b. So keep in mind, this is not vector a and b that are perpendicular. It's a linear combination of them. Now, we also have one other given that's going to help us when applying the dot product. And we want to find the angle between A and B, again, which we're going to find from the dot product. So since these two vectors are perpendicular, then A plus 3B dot product 4A minus B is equal to 0. Now we use the distributive property first here, and I'm going to rearrange here to get, I'm distributing A here, so A dot product 4A minus B, and then 3B dot product 4A minus B, which is exactly what we see here. And this is equal to 0. And now I'm going to apply the distributive property one more time with each of these brackets, and I will get here 4A dot product A and A dot product negative B, and here we have 3B dot product 4A and 3B dot product negative B. And you see all of these 4 dot products here. And now I'm just rearranging a little bit using associative and commutative properties here. So, and keep in mind, the associative property is used for the scalars, not for the dot product itself. So then, here I have for A dot product A, here we have A dot product B, and here's B dot product A, and here B dot product B. So remember, these, and again, I'm not counting the scalars because the scalars are going to be applied at the end. So these two are important because they are just my magnitude property. So here I have magnitude of A squared, and then here we have magnitude of B squared. And these two, Again, A dot product B and B dot product A are the same. So here I've just combined them into 11A dot product B. Now, this is just the dot product. So magnitude of A, magnitude of B, and then cosine of theta. And again, this is all equal to 0. So I have two different magnitudes here, and they're unknowns. So what I'm going to do is now use that given that the magnitude of A is 2 times the magnitude of B. And substituting that value for everywhere that I had an A, I end up with, and I've just worked it out here, a simplified expression, which is 16b squared plus 22b squared cosine of theta, and then minus 3 times b squared. And here I can just combine these two. It's 13 times square root of b, magnitude of b squared. And I'm solving for cosine of theta. So I've moved that expression to the right-hand side. And then I divide by the coefficient here, which is 22 magnitude of b squared. And these two magnitudes, and they're positive as well, so they're going to cancel out, and I'm left with negative 13 over 22. And since b is non-zero, this was an important feature as well. I can do this canceling out because I'm not getting an indeterminate case. And finally, theta is 126.2 degrees. So then we say the angle theta between non-zero vectors A and B is 126. And again, remember, this came from the dot product over here, which was A dot product B, which by definition, theta is the angle between vectors A and B. And now we're going to extend to algebraic vectors. So now, given A in component form with A1 and A2, B as B1 and B2, and the angle between them is theta, then here, all we're doing is, for the dot product, we have that same definition, but now this is equal to A1 B1 plus A2 B2. Now, in R3, it's the same, but now we have to account for that third component. So this is equal to A1B1 plus A2B2 plus A3B3. So a little bit different now, but it's actually going to be a lot more helpful for us when we are working with algebraic vectors because we have a simpler operation here. And again, because these are components, the components are values in the set of real numbers, then this is just a scalar. So the dot product is still a scalar here. And the properties of the algebraic vectors work the same as the dot product. So with respect to here, the same things that we could do up here, it's the same. So you can have commutative, distributive, the magnitude property, and so on. And what that looks like for our diagram, just to show you. Oh, sorry, not for the diagram there. But this is another type of question that you will see when working with the dot product. And we already did do an example of it, but it's to find the angle between two vectors. But now this is expanded to three-dimensional space. So given two vectors A and B, we can find that the angle between them, we start with cosine of theta from the definition of the dot product, which is the dot product of A dot B, and this is divided by the magnitude of A and the magnitude of B. And remember, the magnitude of A and B is just the square root of each of the terms squared and added together. So for example, given A and B here, we're asked to calculate A dot product B. And we have now two vectors in three-dimensional space. And finally, we're going to, after we find the dot product, use it to determine the angle between A and B to the nearest degree. So from the definition of the dot product for algebraic vectors now, this is equal to the x components multiplied plus the y components multiplied and the z components multiplied. And this will give you 17. Now we find the magnitude of A and B, which is square root of 21 for A and square root of 34 for B. And now using this definition here, we have cosine of theta, which is the angle between them, is the dot product of A and B, which was 17, divided by the magnitude of A and magnitude of B, which was square root of 21, square root of 34. And we get 0.6362. So to find theta, we're just taking the inverse of the cosine function, which gives me an angle of 50.5 degrees. So then the angle between vectors A and B is 50.5 degrees. We can also be asked this question, that you'll see these types of questions as well. So for what values of m are the vectors p and q perpendicular? So p is given by m, -3, and q is given by m, -3, 6. So here we're using the dot product of algebraic vectors, which gives me m squared, m times m, and then m minus m times a -3, which is -3m, and then -3 times 6, which is -18. And this has to be equal to 0 for these to be perpendicular. But this is just a quadratic function equal to 0. So we can solve by factoring. So factoring gives me m minus 6 and m plus 3, which is equal to 0. So then m can be equal to 6 or m can be equal to -3. And I really suggest here you do try this for yourself. But for example, if we do 6, m is 6, then p is 6, 6, -3, and q will be 6, -3, and 6. And if you do p dot product q, you'll get 6 squared minus 6 times -3, and then plus -3, 6, and this will give you 0 here because we have 36 minus 18 minus 18, which is equal to 0. And again, now you can check it for m is equal to -3, but by the same process, you should get also the dot product is equal to 0. So now you've seen the dot product for both geometric and algebraic vectors and different types of questions that you might see with them. So please complete the extra practice questions here, and you do have a practice set on Google Classroom. And as always, don't hesitate to reach out if you have any questions. And again, don't forget that simulation that I added for you for this lesson. It really helps visualize the concept of dot product more. And I will see you all next class.